In this video, I will demonstrate how one can determine if a molecule is polar or not. To do this, there are two main ideas that need to be introduced. The first is bond polarity. This describes the polarity of any particular bond in a molecule, but it does not necessarily correlate to molecular polarity, to the molecule being polar itself as one single entity. I'll explain that with future examples to illustrate the point, but a bond can be polar, a molecule can have polar bonds and not be polar itself. That's just a good point to know at the beginning. And secondly is molecular polarity, this is the conventional idea when you think of polarity. You want to know if the molecule is polar or not. So you need to use bond polarity to determine if the molecule is polar. So now let's talk about the difference between the two. So first, bond polarity. Bond polarity exists, or it's present in a particular bond if there's a difference in the electronegativity between the two atoms in that particular bond. So, as an example, let's consider this generic molecule AB. This AB bond is going to be polar if there is a difference in electronegativity between atoms A or B. So there's only two possible situations with that. Is either A is more electronegative than B, or B is more electronegative than A. Just as a note, En refers to electronegativity in this case, and you'll see that throughout the rest of this video and future videos. So if these situations are present, either of these possibilities, then the AB bond is polar. And as a result, there is a dipole, and the dipole will move towards the more electronegative atom. And I'll illustrate this with the next example of how you can draw a dipole and understand what it is in its entirety. But a dipole is a way to illustrate the polar bond and the qualitative flow of electrons that are in that particular bond. The next big idea is electronegativity. We cannot determine if a bond is polar if we cannot identify if there's a difference in electronegativity between two atoms. So that is what we need to be able to do. So first, let's define electronegativity. Electronegativity is a relative measure of an atom's ability to attract electrons, and specifically, it is the ability for an atom to attract electrons that are a part of a shared covalent bond. So what that means is, like for example, in our molecule AB that we had here, if there's a difference in electronegativity, let's say A is more electronegative than B, A can steal or hog more of the electrons in this bond than B. Remember, a covalent bond is composed of two electrons that are shared between A and B, but it doesn't have to be an equal sharing. A is, in this case, if it's more electronegative than B, it will be taking more of the electrons more often than not, and that is what we define as electronegativity. There are inherent abilities for every atom to be able to do this kind of thing. So, with that, how do we then determine the inherent electronegativity of any atom? And it's relatively easy if you remember this periodic trend. So, electronegativity increases as you move up and to the right on the periodic table. So up and to the right. So if we look at our periodic table of elements, what I'm referring to here with this trend is as you move up and to the right, you're increasing the electronegativity of that atom. So one point to make before I explain which atom is the most electronegative is that noble gases for periodic trends generally are not considered because they, as we know, they are extremely stable because their valence shell is full. And we know that most of the chemistry and chemical reactions that are occurring here that we're talking about occur on the valence shell level. The electrons in the valence shell are interacting with electrons in the valence shell of another atom. That doesn't occur as freely in these noble gases because they already have their valence shell and they're already stable. There's no driving force for them to interact with other atoms. So they generally don't. So with that, it means that they don't have an inherent electronegativity because there's no need for them to take more electrons in a covalent bond because they're already satisfied with their full shell. But if you consider something like fluorine, Fluorine has 7 electrons in its valence shell. So if it gains one more electron, it would have a full octet and be more stable than the 7 electron original state. So because of that, there's a strong driving force for fluorine to gain more electrons, to gain one more electron specifically. So if it's involved in a bond, then that fluorine is going to have more of an ability to hog the electrons than whatever is bound to it. So with that explanation, we now know that fluorine is the most electronegative atom. We do not consider group 18, which is the noble gases. So the group furthest to the right and up is fluorine. That is the atom that's most to the right and up. So it is the most electronegative. And then oxygen and chlorine are similar, and so on and so forth. In most of the molecules that you'll see, there'll be a rather large difference between the location of the atoms that are involved in the bond. So it'll be rather easy to determine if there is a difference in electronegativity. For example, a common bond is carbon-oxygen or carbon-chlorine, carbon-sulfur. All of these would be enough of a difference in the distance that this trend would be sufficient to identify that there's a difference in electronegativity. So now, with that, let's work on an example to illustrate all of these points together in one problem. So my question here is to determine if there are polar bonds in hydrofluoric acid, HF. So first thing you have to do for any of these polarity questions is draw the Lewis dot structure. So we know that hydrogen, in this case, is just singly bound to fluorine. And we know that fluorine must have 6 electrons around it to fulfill its octet. We know hydrogen is one of the exceptions that only needs 2 electrons to be full in its octet. So now we have to look at our periodic table to determine if there's a difference in electronegativity. So we take a glance at our periodic table. We see fluorine in group 17 or 7A, hydrogen all the way over here on the far left in group 1. So from that, we know that there is a difference in electronegativity. And specifically, fluorine is more electronegative than hydrogen. So now what we know is that this is a polar bond. HF is a polar bond, which also means that it has a dipole. So HF is a dipole. There's a dipole present, is what we can write. So now how do we illustrate this dipole? So dipoles always go from positive to negative. So towards the more electronegative atom. So if we look at HF, we know that fluorine is more electronegative. So the dipole that we would draw would be like this, moving from hydrogen to fluorine in the direction of the more negative atom, the more electronegative atom. So the other thing you can do with dipoles is draw these partial charges. So this is the Greek letter delta, lowercase delta. It just represents partial, so delta is partial. So from the difference in electronegativity in the presence of this dipole, we know that there is a difference in the sharing of the electrons. So to illustrate this, we write that there is a partial negative on the fluorine and a partial positive on the hydrogen because it has less of the electrons and fluorine has more of the electrons. So this illustrates that there is a polar bond in hydrofluoric acid, and then this is how you would draw the dipole to illustrate the bond polarity, and then you can take it one step further and draw the partial charges. So this idea will be used over and over again to determine if a molecule is polar. So now the next thing to talk about is this idea of molecular polarity. So molecular polarity is a molecule is polar if the sum of the polar bonds or dipoles is non-zero. So this is why I introduced bond polarity first, because you have to be able to draw all the dipoles, understand the bond polarity to then add them up and determine if the molecule itself is polar. So this is very difficult to understand in words, so I'm just going to move straight into the next example to illustrate what I mean by adding up the dipoles. Because as we just saw, the dipole is an arrow or a vector, so you have to be comfortable with adding vectors to determine if there is a polar, if the molecule itself is polar or not, if the molecular polarity exists in that molecule. So the next question is just determine the polarity of carbon tetrachloride, which is CCl4. And the first thing you have to do for any of these polarity problems is draw the Lewis dot structure. So we know that this is just carbon with 4 chlorine atoms around it. And we know that each chlorine atom has 6 electrons, 3 lone pairs. And now we'll take a look at our periodic table to determine if there's a difference in electronegativity. We see a chlorine is here in group 17 and carbon is here in group 14. There is a difference in electronegativity, again using our periodic trend. So we know that chlorine is more electronegative than carbon. So we know that all of the dipoles are moving towards the chlorine atoms away from the carbon. So it doesn't matter where you start, there's a carbon dipole going away from the carbon here, away from the carbon here, towards the chlorine, here, and here. So, and then we can also do our partial charges, like we talked about in the previous question with the dipoles. So we know that chlorines are all going to be partial negative. Again, the dipoles move from positive to negative. So the carbon then is partial positive. So this looks like a mess here now, because there's a lot of atoms in this particular molecule. But all you have to think about to determine if the molecule is polar is add up these vectors. So whenever you add a vector, you just add up the tip to tail. So let me illustrate my point here. For this example, it's rather trivial, but other ones it might not be. But if you wanted to add up this and this, you see that they clearly are going in the opposite direction with the same magnitude, so this would be 0. I'm adding up the one going left and the one going right. You can make the same argument for the one going up and the one going down, so the sum of all these dipoles is 0. So this is in fact nonpolar. So it's important to know this molecule is nonpolar even though there are polar bonds. In fact, there are 4 polar bonds and there are 4 dipoles present in carbon tetrachloride, but the dipoles add up together to a 0 result, so the entire molecule is therefore nonpolar. Hopefully this is making sense so far. The rest of the video, I'll just work a few more examples, and that'll be it for today. So here again, it's the same question. We're asked to draw the dipoles and determine the polarity of the following molecules. So first we have water. So again, for any of these polarity questions, you have to draw the molecules first, the Lewis dot structure. So a lot of students would incorrectly draw this. So this is correct in terms of the octet rule for oxygen. Hydrogen's happy, everything's satisfied. The problem is this doesn't consider bond angles. And often it doesn't matter. But for this question, I'll illustrate why this can get you in trouble. So it's very commonly known that water is polar. So if it's a molecule you don't know, you have to go through this whole process. But if the question was just, is water polar, it's common that that is something that is just known. So you would just say that's polar. But I'm going to illustrate how you can use this idea of dipoles. With this incorrect structure, you will come to the wrong conclusion. So we know that oxygen is more electronegative than hydrogen. I'm not going to show the periodic table in this case, but you can check for yourself. So we know that oxygen is more electronegative than hydrogen. So there are dipoles going towards the oxygen. So there's a partial negative on the oxygen, partial positive on both the hydrogens. So if you use the same idea that we just talked about before, if you add up these dipoles, you would say it's a 0 result. And then you would say that this is nonpolar. But as I just mentioned, we know that water is polar, so this can't be correct. None of this cannot be right. So this is incorrect. The reason it's incorrect is because you don't consider the bond angles like I mentioned. So the reality of oxygen, it's more has this shape, this bent shape. And it's due to the presence of these two lone pairs that distorts these bond angles and push them down away from the oxygen. So now, again, we have our negative charge on the oxygen, positive, partial positives on the hydrogens, and we draw our dipoles towards the oxygen. And now if we add these up, we get a up arrow. So I'll illustrate this again, how we add up vectors. So if I want to add this plus this, the sum of this equals this. So what you have to do is you pick one of the vectors to stay unchanged. So I picked this one and I just moved it over here. And then this one now, you have to translate this in space from tip to tail. So tip of this one that we just copied over, and you translate this in space to here, where again, this is unchanged in direction and everything, but you just move it from tip to tail, tip of this one to tail of this one. And then the sum of them is when you go from the original tail to the new tip of the added vector. So the correct vector, the summed vector, is this up arrow. So this is a non-zero vector, so H2O is polar. So the reason I go through that is to illustrate that bond angles are extremely important even in concepts like polarity. You need to be able to draw the molecule close to how it actually is in three-dimensional space to determine the correct dipoles and the correct polarity of the molecule. So next, we're going to work through a few more examples. So the next molecule we have is NH3. Same question, draw the dipoles and determine the polarity of the molecule. So we have NH3, so we draw our Lewis dot structure to start. We have nitrogen, single bound to 3 hydrogens, and 1 lone pair. So now consider the lone pair again. This may distort the geometry. We need to consider that. So just like we had to in water. In water, however, there were 2 molecules, or 2 lone pairs. That will distort the angles even more. But there's going to be some distortion here. So we just want to be thinking about that. So next, we'll look at our periodic table. We see nitrogen is more electronegative than hydrogen. So with that idea, then, we know that we can draw dipoles towards the nitrogen. So we know there's a partial negative on the nitrogen and partial positives on all the hydrogens. And we go dipoles towards nitrogen. So the reality of this shape is it's like a spoke of the wheel. So what it really looks like is there's a nitrogen on the top, and then there are 3 coming out in like a tripod configuration, because that puts the lone pair away from it all. But the reality is that this doesn't change these bond angles or the dipoles. So it's okay to represent it like this, but you just need to be thinking about it, because when it does matter, you'll need to know, and when in this case it doesn't matter, so it's fine to represent it like this. So now you add up the dipoles, so the ones going right and left cancel, so the overall dipole then is just the up dipole from this hydrogen to this nitrogen, so that's a non-zero result, so this is a polar molecule. It has polar bonds and it's polar. Okay, and the last example we'll work is carbon dioxide, CO2. So again, Lewis structure. So it's a carbon double bound to 2 oxygens. So we'll look at our periodic table. We see that oxygen is more electronegative than carbon. So these are partial negative. Carbon's partial positive. Dipole going away from the carbon atoms. And now, at first glance, you would think that these dipoles cancel, And you'd be right, that is correct. But you need to always consider the shape. Is the shape going to be distorted by lone pairs or anything of that like that would cause it to end up being polar by chance? And in this case, carbon has no lone pairs, and this is the center of the molecule that we're referring to. There's no lone pairs there. So this is in fact just a linear molecule in a straight line like shown. These lone pairs have no need to distort this angle because they're already very far away from the double bonds in all of the cases. So this is the correct geometry, correct shape. So therefore, these dipoles would cancel. They're pulling in opposite directions with equal strength. So the sum of that would be no dipole. So this is a nonpolar molecule. Again, this has polar bonds because there is these dipoles, but their sum of the dipoles results in a nonpolar compound. So that's all I have for you guys today. Please feel free, if you enjoyed the video, to leave a like and subscribe to the channel for more content like this. If you have any specific questions that I didn't touch on or an idea that you would like me to explain in a future video, please leave a comment. Feel free to do that, and I'll try to get to as much of the questions as possible. So with that, I hope you have a good day, and we'll see you in the next video.